Okay, folks, welcome to the Graphics Programming Virtual Meetup. Today we will talking about the physically based rendering book, and we start reading chapter 10 about textures. So we had BRDFs and BTDF last semester. Last chapter, which addressed only parts of the problem of describing how the surface scatters light. So although they describe how light is scattered at a particular point on the surface, the renderer needs to determine which BRDF and BTDF are presented at the point, and also what their parameters are. And I think this is mostly material. Well, I guess also you can encode texture information, encode this information on texture, and yeah, and this is mostly texture, I think. In this chapter, we'll describe a procedural shading mechanism to address this issue. So there are two components in PBRT's approach: textures, which describe the spatial variation of some scalar and the spectral value over a surface and material, which evaluate texture at a point on surface in order to determine the parameter for their associated BSDFs. So separating the pattern generation responsibility of texture from the implementation of reflection models via materials make it easy to combine them in arbitrary way. Yes. So they just make it easier to create a wide variety of appearances. In PBRT, a texture is a fairly general concept. It is a function that maps a point in some domain to value in some other domain. So it's basically a function. It's a definition of a function, basically.
Yeah, I noticed that. Very simple.
Yeah.
This chapter will be quite short then, I bet. Haha.
A variety of implementation of texture classes are available in the system. The PBRT has textures that represent zero-dimensional function. Just no input. That means there's a constant. To accommodate surfaces that has the same parameter value everywhere. And also, that's most commonly used image map textures are two-dimensional functions that use 2D array of pixel value to compute the texture values at particular points. They will not be talked in today, but in later section 10.4. There are even texture functions that compute value based on value computed by other texture functions. So texture may be a source of high frequency variation in the final image. Yes. So figure 10.1 shows an image with severe aliasing due to texture. Because the frequency is so high, our sample rates just don't keep up with that high frequency, and that will cause a problem of aliasing like this. Although the visual impact of this aliasing can be reduced with non-uniform sampling technique from chapter 8, a better solution to this problem is to implement texture functions that adjust their frequency content based on the rate at which they are being sampled. For many texture functions, computing a reasonable approximation to the frequency content of anti-aliasing in the manner are not too difficult, and substantially more efficient than reducing aliasing by increasing the image sample rate. Yeah, just if we have this, because we know the information about the texture, so if we just having this information and deal with it accordingly, it's much better just using general technique for everything basically. This is an example of texture aliasing. The left is no AA, which is look very bad, and red looks alright basically. You prefilter its function and remove high frequency details. The first section of this chapter will discuss the problem of texture aliasing and general approaches to solve it. We will then describe the basic texture interface and illustrate its use with a variety of texture functions. After the texture have been defined, then the last section introduces material interface and number of implementations. So basically, today we will focus on texture aliasing. So expect a lot of math. So yeah, the sampling task from chapter 8 was frustrating one since the aliasing problem was known to be unsolvable from the start. Yes. The infinite frequency content of geometric edges and hard shadows guarantee aliasing in the final images, no matter how high the sampling rate is. So our only consolation is that the visual impact of the remaining aliasing can be reduced to objectionable level with a sufficient number of well-placed samples. But fortunately, things are not this difficult from the start for textures, because there is often a convenient analytic form of the texture function available, which makes it possible to remove excessive high frequency before even sampling it. Or it is possible to careful when evaluating the function so as not to introduce high frequency in the first place. I guess this is MIF map. Yeah. And when this problem is carefully addressed in texture implementation, as is done through the rest of the chapter, there is usually no need for more than one sample per pixel in order to render image without texture aliasing. Of course, other kind of aliasing cannot still be solved this way. Two problems must be addressed in order to remove aliasing from the texture image. The sampling rate in the texture space must be computed. The screen space sampling rate is known from the image resolution and the pixel sample rate, but here we need to determine the resolution sampling rate on a surface in the scene in order to find the rate at which the texture function is being sampled. Yeah. And I guess this is non-uniform on the different part of, I think you just will read later and see what they talk about. Giving the texture sampling rate, the sampling theory must be applied to guide the computation of a texture value that does not have higher frequency variation than can be represented by the sampling rate. By removing excess frequencies beyond the, don't know how to pronounce that, the limit of the texture function. Yeah, but basically this is like twice the sampling rate, I think. Just because, yeah, if we have a frequency beyond that, it will definitely cause aliasing, basically.
I've heard that the Nyquist is how you pronounce it.
Okay. Finding the texture sampling rate. So consider an arbitrary texture function that is a function of position. Defined on a surface in the scene. So if we ignore the complication introduced by visibility, so yeah, another object may occlude the surface as nearby image samples, or that the surface may have a limited extent on the image plane. This texture function can be expressed as a function of a point x, y on the image plane. Then the fxy is the function that maps the image point to point on the surface. And yeah, tfxy gives the value of the texture function as saying an image position xy. So as an example, consider 2D texture TST applied to a quadrilateral that is perpendicular to the z-axis and has corner at wood space at point 0, 0, 0, 1, 0, 0. Okay. If an orthogonal camera is placed looking down at the z-axis such that the quadrilateral precisely fills the image plane, and if the point P on the quadrilateral are mapped to the SD texture coordinate by just basically the whole texture fills the whole image plane, basically direct mapping, and then the relationship between ST and the screen XY is straightforward. S is X divided by XR. Image resolution.
That's it's a very fun way to describe mapping from 0 to 1 to 0 to image resolution. It's very formal, but it does describe it exactly.
Yeah. So here gives sample spacing of 1 pixel in the image plane. This sample spacing in ST texture parameter space is 1 over XR, 1 over YR. And the texture function must remove any detail at a higher frequency. Then can be represented at that sampling rate. Yes. So this relationship between pixel coordinate and the texture coordinate, and thus relationship between their sampling rate is the key bit of information that determines the maximum frequency content allowed for the texture function. Slightly more complex example give a triangle with UV texture coordinate and all its vertices and viewed with perspective projection. It is possible to analytically find the difference in the UV across the sample point on the image plane. And this approach was the basis for texture AA in the graphics processors before they become programmable. For more complex in geometry, camera projection, and mapping to texture coordinates, it is much more difficult to precisely determine the relationship between image position and texture parameter value. We don't even do orthogonal and perspective in PBRT. There are some like camera with lenses, stuff like that. So. Fortunately for texture AA, we do not need to be able to evaluate the fxy for arbitrary. What is f again? Sorry. Map from image point to the point on surface. Okay. We do not need to be able to evaluate fxy for arbitrary xy, but just need to find the relationship between changing pixel sample positions and the resulting change in texture sample positions at a particular point on the image. This relationship is given by the partial derivative of the function partial f, partial x, partial f, partial y, yeah. And this can be used to find the first order approximation to the value of f. If these partial derivative changes slowly with respect to distance x prime minus x and y prime minus y. This is a reasonable approximation. More importantly, the values of this partial derivative give an approximation to the change in the texture sample position for a shift of 1 pixel in the x and y direction, respectively. Yeah. And thus directly yield the texture sampling rate. For example, in the previous quadrilateral example, yeah, if we know the partial derivative, we're done basically. So the key to find the values of this derivative in general case lies in the value from the rate differential structure. Okay, we should define in section 3.6.1. interesting. And something to look at later. And this structure is initialized for each camera array by the generate ray differential method. It contains not only the ray being traced through the scene, but also two additional rays will offset horizontally when pixels sample from the camera ray and another offset vertically. All the geometric ray intersection routines use only the main camera ray for their computations, but the auxiliary ray are ignored in this case. But we can use those offset rays to estimate the partial derivative of mapping xy from the image position to wood space position. And the partial derivative of mapping uxy and vxy from the xy to the UV parametric coordinates, given the partial derivative of rendering space position, partial p partial x and partial p partial y, and the derivative of UV parametric coordinates, partial u partial x partial v partial. So I'm a bit lost on this paragraph. We have 6 values on the surface interaction. Those are the gradient of the point P regarding the x and y screen space coordinates, and those are like the UV, the partial of UV regarding x and y. Yeah, I think I understand this now. Sometimes this code is much easier to read than this paragraph. I guess it's basically the types. So the surface interaction compute differentials method computes these values, and it's called by surface interaction getBSDF before the materials getBS method is called, so that this value will be available for any texture evaluation routine that are called by the material. The ray differentials are not available for all ray traced by the scene. Rays starting from light source traced for photon mappings or bidirectional path tracing. Further, although we will see how to compute ray differentials after rays undergone specular reflection and transmission in section 10.1.3, how to compute ray differential after diffuse reflection is less clear. In cases like those, or as well as corner cases where one of the differential's direction is perpendicular to the surface normal, which lead to undefined numerical value in the following. An alternative approach based on approximating the ray differentials of the ray from the camera to the intersection point is used. Okay, so basically if we has ray differential and dots of normal and ray direction, that normal does not align with x and y direction. And so a comment, I wonder how much accurate differentials for diffuse rays impact the image. I can't imagine it's that significant. I don't know. Yeah, but anyway, so if we don't have ray differential, we use the alternative approach. The key to estimate the derivative is the assumption that the surface is locally flat with respect to the sampling rate at the point being shaded. The reasonable approximation in practice, and it's hard to do much better. Yeah, because ray tracing is a point sampling technique. We have no additional information about the thing in between the ray we have traced. For highly curved surfaces or at another word I don't know how to pronounce. Sorry. So this approximation can break down, though it's really a source of noticeable error. So because surface is flat, we can have a plane to a point P intersected by the main ray that is tangent to the surface. So the plane is given by this implicit equation. Where ABCs are just components of normals, and D is normal dot the point. We can then then compute the intersection point px and py between the auxiliary ray Rx and Ry and this plane. These new points give the approximation to a partial derivative of position on the surface, partial p, partial x, and partial p, partial y, based on the forward differences. Yeah. Of course, the differential rays are offset 1 pixel sample in each direction. There's no need to divide these differences by the delta value. Yeah, because delta is just 1. Why they calculate the p twice, or it's just a getter function? Okay. Okay, yeah, replane intersection algorithm described in previous section gives the t value where we describe by origin O and direction the intersect the plane described by ax plus b, by plus cz plus d equal to 0. So yeah, we basically just use this. We will, just for the sake of time, not to delve deeper into this, but anyway, yeah, we just calculate. So to compute this value for two auxiliary rays, we first compute the plane's d coefficient, and we don't need to compute ABC because they are normal basically, and then we can then apply the formula directly. Yeah, to get the px and py, and then we do this. For cases where ray differentials are not available, we will add a method to the camera interface that return approximate value of partial p, partial x, and partial p, partial y at point on surface in the scene. This should be a reasonable approximation to the differential of the ray from the camera that found the intersection at a given point. Camera's implementation of this method must return a reasonable result even for points outside their viewing volumes, which they cannot actually generate rays. Camera base provides an implementation of approach to approximating these differentials that is based on the minimum of the camera ray differentials across the entire image. Because of all of PBRT's current camera implementation inherits from camera base, the following method take care of all of them. Compute tangent plane equation for ray differential intersections. find the intersection point for approximated camera differential rays. And then estimate partial in tangent plane at the intersection point. This method starts by orienting the camera so that the camera space, the axis is aligned with the vector from the camera position. To the intersection point. Then use the lower bound on the spread of ray over the image. Data provided by the camera to find the approximate differential rays. Then intersect these rays with the tangent plane at the intersection point. Yeah, so first we reorient the camera to point at the provided intersection point. And in camera space, the ray to the intersection that has the origin 0, 0, 0 and the direction 0, 0, 1. And the extent of ray differential on the tangent plane defined by the surface normal at the intersection point can then be found. So this is a visualization of camera-based approximate dp dxy. They represent the filter area as a product of max partial u, partial x, partial u, partial y. And then visualize the base to a logarithm of the ratio area computed by the two technique. Log2 ratio generated by greater than 0 indicates the camera-based approximation estimated a larger filling area. Okay, yeah, so we want to be close to 0. And I think 1 or -1 means just we don't have a very good approximation. There are a number of sources of error in this approximation. Yeah, it does not account for how light was scattered at intermediate surface for multiple bounces repassed because we just use camera directly. There's also the fact that it's based on the minimum of camera's differential for all rays. It tries to underestimate those derivatives rather than overestimate them, as we prefer aliasing over blurring here. The former error can be addressed with additional pixel samples. Yeah, blurring just, yeah. So yeah, the previous figure has visualization that compares the local area estimate by those derivatives at intersection to the area computed by using the actual ray differentials. And yeah, most point is okay, but think the ceiling and also somewhere in here is just not as good. First step of the algorithm, we have intersection point in rendering space P that we would like to transform into a coordinate system where it is along the z-axis with camera at origin. Transform to camera space get us started. The additional rotation that transform the vector from the origin to the intersection point to be aligned with the z finish the job. The d coefficient of plane equation can be found by taking the dot product of the transformed point and the surface normal. Yes. X and Y components of the transform points are equal to 0. The dot product can be optimized to a single multiply. Oh yeah. X, Y, and Y are zeros. First find the point in the camera space, and then we create a transformation to transform this point to 0, 0, 1. And yeah, we transform this. Shouldn't this just be 0, 0, 1? Anyway, yeah, also we transform the normal. And camera implementation that inherits from camera base and use this method must initialize the following member variable with values that are lower bound on each of their respective position and direction differentials over all the pixels in the image. Just minimum differentials. And the main ray in this coordinate system has origin 0, 0, 0 and direction 0, 0, 1. Adding the position and direction differential vector to those give the origin and direction of each differential ray. Given those the same calculation as earlier, give us the t-value for the ray plane intersection for the differential rays and then the intersection point. And it's the same as this. For an orthogonal camera, those differentials can be computed directly. There are no change in the direction vector, and the position differential are same at every pixel. and their value are already computed in the orthogonal camera constructor, can be used directly to initialize the base class member variable. Yeah, direction don't change. And this is just a constant. All the other cameras call find minimum differentials, which estimate these values by sampling at many points across the diagonal of the image and store the minimum of the differentials encountered. Okay. And given the intersection point px and py, partial p, partial x, partial b, partial y cannot be estimated by taking their differences with the main intersection points. To get the final estimate of the partial derivatives, these vectors must be transformed back out into rendering space and scaled to account for the actual pixel sampling rate. So this is in the scale camera rate differential based on the image sampling rate fragment. So we transform from camera back into the render space, and the scaling is the without jitter it's just 1, otherwise it's I don't really understand this, but anyway. A call to this method take care of computing the partial p, partial x, and partial p, partial y differentials in the compute differences method. Yeah. So we now have both the partials, partial p, partial u, partial p, partial v, as well as one way or another partial p, partial x, partial p, partial y. And then finding those should be pretty trivial. I think using the chain rule we can find that. Why there is a 10.1 here? Is something missing? Probably shouldn't look at that, but I think there are equation missing here. Anyway, just like as the last step is just to find those four from the previous information we already know, and they use a little bit of linear algebra, but unfortunately some part of the text is missing, so yeah, maybe let's stop here because it's already an hour. We can read we can read the other part later.